Okay, now the equilibrium test, section 1, multi-choice. Question 1, which of the following statements about the equilibrium constant is correct? Okay, so it's all about the equilibrium constant. Sometimes they call it K, sometimes they call it Kc. You don't need to write the C. So, what are things that we should know about K? Now, the main thing that we should know about K is K tells us the relative proportion of reactants to products at equilibrium. So, specifically, if K is much more than 1, and we write like 2 greater than signs to show that if it's much more than 1, it means that the concentration of products is greater than the concentration of reactants at equilibrium. It's important to realize that this is at equilibrium. In the same way, if K is less than 1, it means the concentration of products is less, or basically the concentration of reactants is more than the concentration of products. And if K equals 1, that means the concentration of reactants is approximately equal to the concentration of products, but only approximately, not exactly. All right? And the reason why not exactly, now just think about it. I'll just give an example. So let's say we have a reaction such as, let's keep it a very simple one. So let's say we have 2A becomes B, and let's pretend they're both gases. So we obviously include both, we don't even have a second species. So 2A becomes B. Both 2A and B are gases. Now let's assume, let's come up with an expression for the equilibrium constant. The equilibrium constant would be the concentration of B divided by the concentration of A squared. And let's let it equal, for argument's sake, let's let it equal to 1. So I'm trying to figure out what happens if K equals 1, and I'm trying to show why it's approximately equal and not exactly equal. So if this equals to 1, if we rearrange it, that means the concentration of B is concentration of A squared, which effectively means that the concentration of A is square root of the concentration of B. So you can clearly see that despite the equilibrium constant being 1, the concentration of the species were not equal. In fact, concentration of A is square root of B, which is kind of equal. That's why I've got an approximate sign, but really not equal to each other. Okay, so that's important. Now, what else is something that we should know about K? I mean, obviously the main thing that we should know about K is it tells us the relative proportion of reactants to products. Something else that we should know about K is that K is independent of reaction rate. K is independent of reaction rate. It has nothing to do with the reaction rate. And obviously, what is K dependent of, or what is K affected by? So K is dependent on temperature. We should definitely know that temperature affects the K value. These are the main things we should know about K. There are a few things here and there we should know, but these are the main things. Okay, so let's have a look at this question. Which of the following statements is correct? If K equals 1, there are the same amount of products and reactants once equilibrium is established. Now, we just agreed it's not necessarily the same, it's just approximately equal. So even though that answer is almost correct, it's not quite A. A large value of K indicates a high rate of forward reaction. I just said that K is independent of reaction rate, so B is not true. Well, now, what did I say is the only thing that affects K? Temperature. All right, K is only affected by temperature for a specific equation or reaction. So it says the value of K will change if the volume of the reaction vessel is reduced. Now, that is not true. A change in volume will not affect the K value. Only temperature affects the K value. So C is not true. All right, I really should say K is dependent on temperature only for a given reaction / equation. Okay, so it's not C. And then lucky last, the value of K will change if temperature is decreased. Yes, we agreed that a change in temperature will affect the K value, so therefore that statement is correct, so the answer is D. Okay, question number 2. Which of the following systems below is not a closed system? Now, make sure you guys understand the 3 types of system that we have. We have an open system. When you have an open system, it means you can have transfer of matter and energy, all right, from system to surroundings, okay? from two systems and surroundings. Okay, that is what we call an open system. A closed system is where there is no transfer of matter to and from the system, no transfer of matter, only energy. Now, these are the two that we deal with in chemistry, all right? Now, there is one in physics that we deal with. There's an open system, there's a closed system, and then there is an isolated system. The whole purpose of an isolated system is no transfer of matter or energy. No transfer of matter and energy. Okay, not just or, and energy. So those are the three systems. Great. And now really the only one that you can truly establish equilibrium is in a closed system. Only in a closed system. I mean, I guess theoretically in an isolated system we could as well, but remember we're dealing with the chemistry ones, and in chemistry these are the two that we deal with, and out of these two, out of the open and closed system, only in a closed system can we reach equilibrium. So we're not gonna worry about isolated system in chemistry. Okay, and I guess at the end of the day, isolated is a we're not going to worry about isolated system. Okay, so back to the question, which of the following is not a closed system? Not a closed system means open system really, and open system means that we have a transfer of matter is allowed. So a sealed glass cylinder containing a mixture of nitrogen dioxide, and dinitrogen tetroxide. Okay, it's a sealed glass container containing two gases. I guess that means no transfer of matter. And if it's no transfer of matter, it is a closed system. So the answer is not A, because we want which one is not a closed system. The exothermic reaction between marble chips and hydrochloric acid. Now, unless they said the stoppered conical flask, then theoretically CO2 could have escaped. Yes, we could have had CO2 escaping. However, that's what happens, right? Acid plus a marble chips, for those that don't know, is just calcium carbonate. So acid plus metal carbonate is salt plus water plus CO2. If it was not stoppered, the CO2 could escape. If the CO2 can escape, we would have said it's an open system because it allows for a transfer of matter, but it is stoppered, so therefore it is a closed system, and therefore the answer is not B. Next one, an ice cube melting on a watch glass. Okay, so if an ice cube melts, you can imagine on a watch glass at room temperature. So that is definitely not a closed system, because if we have an ice cube, so that's basically solid ice, is turning into, I really should write double arrow to show that there's an equilibrium, because it could go back the other way and condense again if it wanted to, but the solid ice can become a liquid ice. And remember, what can liquid ice do? Liquid ice can evaporate. Some of that liquid ice can go ahead and become a gas, and the fact that it can become a gas implies that it's going to escape into the atmosphere, and the fact that it escapes into the atmosphere means that it is not a closed system. So effectively C is the answer. Okay, and lucky last, it says an unopened can of carbonated soft drink. Again, it's unopened, so the fact that it's unopened means that none of the CO2 can escape. So you can have some of the CO2 gas inside there. It can evaporate. Okay, so some of the CO2 gas can evaporate and become CO2. I really should write CO2 aqueous. So the dissolved CO2 can evaporate, but because it's a closed system, so I'm going to draw a picture of this. So let's say we have a Coke can, all right, a soft drink can. In a soft drink can, we have basically Coke inside there, or whatever soft drink you have, and there's CO2 that is dissolved in there. There's also CO2 gas. So this forward arrow represents that some of the CO2 can evaporate and become CO2 aqueous, and then the reverse arrow indicates that some of the CO2 gas can basically re-enter the solution and dissolve again and become CO2 aqueous. While the can is closed, it is in a system of equilibrium. It is what we call a closed system where there is no transfer of matter. As soon as you open the can, some of the CO2 gas can escape, and if the CO2 gas can escape, it's what we call an open system, okay? So therefore D is not the answer. And just so everyone understood what keywords were there in the question, this one was a sealed glass cylinder. That gave it away that it's a closed system. This one said stoppered conical flask. That basically gave away it's a closed system. And this one said an unopened can. Okay, so that's closed. Okay, so it's pretty easy concept. Question number 3. An energy profile diagram for a chemical reaction is shown. Okay, so the one thing that I pick up for this is that the reactants are at a lower enthalpy than the products, which basically means that it is a positive delta H, and therefore it is what we call an exothermic reaction. Okay, that's pretty easy, straightforward concept. Okay, which of the following can be correctly determined from this energy profile? The rate of the forward is greater than the rate of the reverse. Now, it clearly says in the question at chemical equilibrium. And if it's a system at chemical equilibrium, it means the rate of forward reaction equals the rate of reverse reaction. So A is just not correct. Okay. Now, decreasing the temperature will decrease the rate of the reverse reaction by less than the rate of the forward reaction. Now, everyone should know that when there is a change in temperature affects both the forward and the reverse reactions, okay? If there is an increase in temperature, there is an increase in both the forward and the reverse, and if there is a decrease in temperature, there is a decrease in both the forward and the reverse. Now, what we need to know is that the endothermic reaction has a higher activation energy, and if the endothermic reaction has a higher activation energy, therefore it is more sensitive to temperature changes. Because of the higher activation energy, it is more sensitive to temperature changes, which means that it is more profoundly affected. Okay? It is more profoundly affected. So what I'm trying to say is this. I'm trying to say if there's an increase in temperature, yes, there's an increase in both the forward and reverse, but the increase in the endo is more profound than the increase in the exo. And if there's a decrease in temperature where both the forward and reverse reaction rates decrease, the decrease in the endothermic reaction is more than the decrease in the exothermic. Okay, so just remember that the endothermic is more sensitive to temperature changes. Okay, so decreasing the temperature. Now remember, this is an exothermic reaction. So decreasing the temperature, we all know that the decrease in temperature will cause a decrease in the forward reaction rate, decrease in the reverse. And I just discussed that the decrease in the endo is going to be more than or more profound than the decrease in the exo. Now we know that the forward reaction is exothermic, so effectively it means the reverse reaction is endothermic. So if the reverse reaction is endothermic, then I can say that the decrease in the reverse reaction is more profound than the decrease in the forward reaction. They both will drop, but the reverse will drop more than the forward. So it says decreasing the temperature will decrease the rate of the reverse reaction by less than the will decrease. I've just realized I've made one error. If delta H is more than 0, it is not an exothermic reaction. If delta H is more than 0, it is therefore an endothermic reaction. Shouldn't have made that error. So let's change that again then. So the decrease in the endo is, so the only mistake I made is here. I wrote delta H is more than 0, and then I wrote exothermic. It was meant to say endothermic. Okay, so let's go back. Yes, decreasing the temperature will decrease the forward and the reverse. Yes, the endo will drop more than the exo because it's always more profoundly affected. The endo is the forward reaction. So what I'm trying to say is the forward reaction drops by more than the reverse. All right, what does this question say? Decreasing the temperature will decrease the rate of the reverse reaction by less than the forward reaction. That's exactly what this says. The decrease in the reverse is less than the decrease in the forward. So therefore, B is the answer. Okay. The activation energy for the reverse reaction is greater than the activation energy for the forward reaction. That's not true. I mean, first of all, we should always know that the endothermic reaction has a higher activation energy. And just for the purpose of learning, this is the activation, or should start at the bottom. This is the activation energy for the forward reaction, and that effectively is the endothermic reaction. We agreed that the forward reaction is endothermic. That is the activation energy for the forward reaction, which makes this the activation energy for the reverse exothermic reaction. Okay, you can clearly see the endothermic reaction as a higher. You can clearly see it has a higher activation energy. Okay, so it says the activation energy for the reverse reaction is greater. You can clearly see this arrow is not bigger than that arrow there, so therefore C is wrong. And the magnitude of the enthalpy change for the reverse reaction is greater than the magnitude of the enthalpy change for the forward reaction. Well, that's not true. When it says magnitude, it means sign doesn't matter. And for any reaction, we should all know that for any reaction, the delta H of the forward reaction, for example, is the for any reaction, the delta H of the forward reaction is negative the delta H of the reverse reaction, aka the magnitude of delta H. Magnitude is by these arrows mean magnitude. So the magnitude of delta H of the forward reaction is equal to the magnitude of delta H of the reverse reaction. This option is claiming that the magnitude of enthalpy change for the reverse reaction is more than the enthalpy change for the forward reaction. That's not true, okay? So B is correct. Next one. The following gaseous system was set up so that the volume of the system could be varied. Fine. The system is initially at equilibrium. At time T1, the volume of the system was halved. Okay, so there was a decrease in the volume. What is decrease in the volume? Specifically, it was decrease in the volume of a gaseous system. Okay, it is a gaseous system. Now, what does a decrease in volume mean? Increase in concentration of reactants, immediate increase in concentration of reactants. So immediate increase in the forward reaction rate. And there's an increase in the concentration of products as well. There's products on the gases side and reactants on the gases side. So if there's an increase in the concentration of products, there is also an increase in the reverse reaction rate. Now, what we need to understand is that there's two gases here and one gas there. There are two gaseous reactants versus one gaseous product. And for that reason, the increase in the forward reaction rate is greater than or more profound than the increase in the reverse reaction rate. And don't forget why that is. The reason being is because reactants do the forward reaction, whereas products do the reverse reaction. Okay, so the fact that there are more reactants than products means that the forward reaction rate increases by a greater amount than the reverse reaction rate, as per collision theory. Okay, until equilibrium, and then basically that means that the forward reaction rate is greater than the reverse until equilibrium is re-established. That's a typical collision theory response. Okay, so in this case, it says the forward arrow is represented by the solid line and the reverse reaction is by the dotted line. So first thing first, when you decrease the volume of a gaseous system and there are gases on both sides, it means both forward and reverse reaction rates immediately spike. All right, so if both forward and reverse reaction rates immediately spike, that would mean that the answer cannot be B and the answer cannot be D. All right, answer can't be B, answer can't be D, because in one of them, this one's not spiking, and the other one, this one's not spiking. So it's either A or C. Now, we just agreed that the forward spikes by more than the reverse, which means the solid line spikes by more than the dotted line, and effectively that means that the answer would be A. Okay, next one. If the volume of the syringe is doubled, which of the following correctly describes the resulting observations? Okay, this one the volume was halved. Okay, so if the volume of the syringe is doubled, so just so you guys understand, the way it works is if we immediately increase the volume, we decrease the concentration of all gas species immediately. And if we decrease the concentration of gas species, there is basically a decrease in the forward reaction rate and a decrease in the reverse reaction rate. All right. In the same way, there are more reactant gases than product gases, which effectively means that yes, they both drop. Yes, both forward and reverse reaction rate drop, but the decrease in the forward reaction rate is more than the decrease in the reverse reaction rate. Okay, the forward, there are 2 gaseous reactants and only 1 gaseous product. So if the forward drops more than the reverse, just remember, if the forward drops more than the reverse, so there's the reverse dropping a little bit and the forward dropping even more, which means that the reverse is more than forward until equilibrium established. The reverse is higher until equilibrium re-established. All right, and another way of saying reverse is greater than forward is that equilibrium shifts to the left. Equilibrium shifts left. Okay, and if equilibrium shifts left, there is going to be an increase in the concentration of NO2 and a decrease in the concentration of N2O4. Okay, increase in concentration of NO2 and a decrease in the concentration of N2O4. If I'm being very technical, there is a, I don't need to be, but I can say it, there will be a partial increase in the concentration of NO2, and there will be a further decrease in the concentration of N2O4. Now, this question is all about observations. So remember, initially, we started off with a mixture of NO2 and N2O4. So we had a brown/colorless gas, okay, which I guess would be brown overall, maybe light brown in color. So immediately, when the concentration of all gaseous species decreased, when the concentration of the brown stuff decreased and the concentration of the colorless one decreased, immediately it became less brown, okay? It became paler brown immediately. All right, and then because we had an increase in the concentration of NO2, there's an increase in the concentration of NO2 and a decrease in the concentration of N2O4. This one's going up, this one's going down, and basically what that means is that caused it to become more brown until equilibrium re-established. So immediately it became less brown, and slowly it became more brown till equilibrium was re-established. So let's check which options are consistent with that. So where's the one where it says that it became less brown initially? So it became less brown initially. The color of the gas mixture will initially be lighter brown. This one also says will lighten. And then what does it say? Then darkens slightly. These ones, by the way, said the color will be more brown. That's not true. The color remains unchanged throughout. That's not true. These two things are true, that the color of the gas mixture will lighten and then darkens slightly. That's what I'm looking for. Then darkens slightly as the reverse reactions favored. That's exactly what we said, that reverse is more than forward, equilibrium shifts to the left, and it becomes more brown. Okay, so therefore the answer is B. Okay, nice. Question number 6. All right, this is the chromate dichromate equilibrium. All right, this is something that we have dealt with quite a bit. All right, so a 5 ml sample was placed in a boiling tube. Okay, so if it's placed in a boiling tube, all right, that doesn't mean it's getting hot. A boiling tube is just a tube where you can change the temperature. Okay, so just think of it as a glass beaker. So which of the following will cause it to become more orange? Now, obviously, to become more orange means an increase in the concentration of this. We want an increase in the concentration of Cr2O72-. Now, the reason why we must have an increase in the concentration of that is for whatever reason, the forward reaction must be favored. All right. So let's consider all the options. Okay, so placing it in a hot water bath. So placing it in a hot water bath basically means an increase in temperature, we know an increase in temperature favors the endothermic reaction to try and counteract the change. And the endothermic reaction, our delta H is negative 42. That means the forward reaction is exo. If the forward reaction is exo, that means we're going to favor the reverse endothermic reaction. We do not want to favor the reverse endothermic reaction. We want something that favors the forward reaction. So therefore A is not correct. Okay. Adding a few drops of concentrated hydrochloric acid. Now, which of these relates to hydrochloric acid? Obviously, the H plus does. So this basically means that they're increasing the concentration of H plus. If you increase the concentration of H plus as per LCP to try and decrease the concentration of H plus, we're going to consume it by favoring the forward reaction. That's a winner, because if you favor the forward reaction, you're going to get an increase in the concentration of the Cr2O72-, causing it to become more orange. Now, obviously, if adding hydrochloric acid works, which is an acid, then adding a base is definitely not going to work. We should have realized the answer was either add an acid or add a base. One of them had to favor the forward reaction. So if adding an acid favors the forward reaction, adding a base neutralizes some of the H plus, which causes the reverse reaction to be favored. So therefore the answer was never going to be D. And why was the answer never going to be C? Now think about it. If you dilute it with distilled water, this one's a little bit more complex, but if you dilute it with distilled water, immediately it becomes, immediately there is a decrease in the forward reaction rate and a decrease in the reverse reaction rate, because you have decreased the concentration of aqueous species. So if immediately there's a decrease in the forward and the reverse reaction, you have to consider how many aqueous species are on both sides. On this side here, we have 4 aqueous species. On the right side, we only have the 1 aqueous species. So yes, there's immediate decrease in the forward and the reverse reaction rate, but due to the numbers involved, the fact that there are more reactants than products, the side with more species is more affected, which means that the decrease in forward is more profound than the decrease in the reverse reaction rate. And if the forward drops more than the reverse, that means the reverse is more than forward. Reverse more than forward, another way of saying reverse more than forward, is favor the reverse reaction. And again, we don't want to favor the reverse reaction. This question wants it to become more orange. It wants us to, as soon as it said become more orange, we should have recognized it meant increase in the concentration of Cr2O72-, aka favor the forward reaction. Okay, so the only one that favored the forward reaction was B. Question 7. Which of the following best explains what would be observed when the temperature of the boiling tube is decreased? Okay, so if we decrease the temperature, we can just use Le Chatelier. We don't have to... Oh, actually, they're both talking about the forward and reverse reaction rates, so I'll use collision theory again because all the options are talking about forward and reverse reaction rates. So if you decrease the temperature, there is a decrease in the forward and the reverse reaction rate. There is a definite decrease in both forward and a decrease in the reverse. Now remember what I said, that in temperature changes the endothermic is more affected. So effectively the decrease in the endothermic reaction is more profound than the decrease in the exothermic reaction. Now delta H is negative, meaning the forward reaction is exo and the reverse reaction is endo. So therefore the decrease in reverse is more profound than the decrease in forward. I'm basically saying that they both drop, but the reverse drops more than the forward. If the reverse drops more than the forward, it means that the forward is more than the reverse. It means that we're going to favor the forward reaction. And if we're going to favor the forward reaction, what does that mean it's going to do? Favoring the forward reaction, again, means it's going to become more orange. We want an option which becomes more orange. So which of these says more orange? So first of all, this one says more orange, and this one says more orange. So it's one of those two that says more orange. What would you observe when the temperature is decreased? Now, more orange, and what did we say? The reverse drops more than the forward. So what does this say? Both the rate of the forward and reverse reaction decrease, that is correct, but the reverse reaction rate drops by more. Yep, that's exactly what we said. So A is the answer. C, even though it's more orange makes sense, it says as the rate of the reverse reaction rate decreases and the forward reaction rate initially remains unchanged. That's not true, they both dropped. So that's the bit that makes this one wrong, the bit where it says the forward reaction rate initially remains unchanged. That statement is incorrect. Okay, so that's why the answer was not C. All right, question number 8. Consider the following systems. All right, if more NH3 is added and equilibrium is re-established. Okay, so if more NH3 is added, obviously the NH3 spikes up. And as per Le Chatelier's principle, to try and counteract the change, the forward reaction is favored. If the forward reaction is favored, the NH3 will partially decrease, the CO2 plus will decrease, and the product will increase. Which means, at the end of the day, the CO2 plus decreased. At the end of the day, the NH3 went up and then came back down a little bit, which means that the concentration of the NH3 still increased at the end of the day, and this one increased. So we're looking for lower, higher, higher. Which one says lower, higher, higher? C says lower, higher, higher. So that is our answer. Question number 9. Which of the following best represents the equilibrium constant expression for the reaction below? Okay, remember we never include solids or liquids, and we always have the products on the top. So K equals the concentration of CO squared divided by the concentration of CO2. We'll omit the solid, so effectively the one that matches is D. D looks exactly like what we just wrote. And question number 10. In which of the following reactions at equilibrium will there be a shift to the left if the volume is decreased? Okay, so that is the change. The change is that the volume of the system is decreased. All right, now remember, we want there to be a shift to the left. Okay, so if we decrease the volume of the system, if there is a decrease in the volume, it means that there is an increase in the concentration of all gaseous species. If there is an increase in the concentration of gaseous species, that means, as per LCP, we will favor the side with less gas. It will favor the side with less gas to decrease the concentration of gaseous species, okay, as per LCP. Alrighty, so the question is asking which one will there be a shift to the left. So we're looking for any option where the left side has got less gas species. We want there to be less gas species on this side and more gas species on the right side. All right, we want something that shifts to the left, so therefore where more gas turns into less gas. So we already have a winner with option A. You can see that there's 2 gases on the left side and there is 3 gases on the right side. So there you go. A shift to the left will convert 3 gases into 2 gases and thereby counteracting the decrease in volume, aka increase in the concentration of gas species. So that's why A is your answer. If you look at all the other options, how many gases on this side? On this side there are 4 gases and on this side 2 gases, so that's not a winner. This one is dealing with aqueous species, so if it's dealing with aqueous species, it's just not relevant. We're only looking at stuff which deals with gaseous species. And then D, there is an equal number of gases on both sides. If there's an equal number of gases on both sides, there will be no, this one specifically, there will be no shift in the position of equilibrium because the increase in the forward reaction rate will equal the increase in the reverse reaction rate as there are equal gases on both, equal gaseous reactants and products. Okay, so that's why the answer was not D. Okay, so the answer is A. That's the end of section 1. Okay, section 2, short answer, question 11. They've given us an equation, write an equilibrium constant expression. Don't forget to write K equals, okay? It's important that we write K equals to. So always products on top, so that would be H2 to the power of 4, CO2. Obviously, we're going to include everything because they're all gases. divided by concentration of H2O squared times concentration of CH4. Okay, pretty easy. Don't forget to write K equals. All right, the graph shows the amounts present of each of the four gases. Okay. Examine the data above, identify the process as endothermic or exothermic, and use LCP to justify your answer. So what I want everyone noticing, it's honestly pretty straightforward. So as we go this way, so as we go to the right, you can clearly see that the temperature is increasing. It's going from 100, 300, 500, etc. all the way to 900. So as we increase in temperature, you should notice two things. You should notice that these things here, the CH4 and the H2O, which just happen to be your two reactants, H2O and CH4, they're your two reactants, they are decreasing in concentration. You can see that they're both decreasing. So I'm just going to write this down. So increase in temperature, specifically in this particular case, what are we noticing? In this particular case, we're noticing that as there is an increase in temperature, we have a decrease in the concentration of reactants, and you can clearly see that what's the H2 and the CO2 doing? Obviously the H2 is doing it significantly more because it's got 4 H2s for every CO2. All right, and what we notice is that the H2 and the CO2 are both increasing. So H2 and CO2, they're both on the way up. So basically there is an increase in the concentration of products. So that's specifically what's happening with the increase in temperature. All right, what generally happens with an increase in temperature? Generally, what happens with an increase in temperature is, according to LCP, it favors the endothermic reaction. It favors the endothermic reactions to basically absorb energy from the surroundings, and counteract the increase in temperature. So in summary, an increase in temperature always favors the endothermic reaction. So generally, I should really write always favors the endothermic reaction, whereas specifically in this case, it is causing an increase in the concentration, a decrease in the concentration of reactants and an increase in the concentration of products. These two are decreasing and these two are increasing, aka it means that the forward reaction is favored. Okay, we are favoring the forward reaction. Perfect. So an increase in temperature always favors the endothermic reaction, and specifically it's favoring the forward reaction. So we can link those two things together. Favors endo, favors forward. Therefore, the forward reaction is endothermic. Therefore, forward is endo. That's exactly what this question is asking. Identify the process as an endothermic or an exothermic process and use Le Chatelier. So I've got a flowchart version of it. I just need to write the flowchart in written words. So we can explain that a decrease as the temperature increases. As the temperature increases, there is a decrease in the concentration of my two reactants. There is a decrease in the concentration of H2O and a decrease in the concentration of CH4, and there is an increase in the concentration of H2 and an increase in the concentration of CO2. So as the temperature increases, the following two things are happening. Therefore, as the temperature increases, this specific equilibrium favors or this specific system favors the forward reaction. If you wanted to be even more specific, you can say that there is specifically a decrease in the concentration of reactants and an increase in the concentration of products. All right, so that's specifically what's happening in this case. Then you can write that an increase in temperature favors an increase in temperature favors the endothermic reaction. Alright, favors the endothermic reaction. We can write as per Le Chatelier's principle. You can't just write LCP in a test, as per Le Chatelier's principle. And we can explain why. That you can explain the endothermic reaction. The endothermic reaction absorbs energy from the surroundings to counteract, in order to counteract the increase in temperature. Perfect. Therefore, put these two things together. The two things are that as temperature increases, we favor the forward reaction, and that an increase in temperature favors the endothermic reaction. Therefore, the forward reaction is endothermic. Perfect. Next, a nickel catalyst is often used. State the effect of a catalyst on a chemical reaction using collision theory. Okay, so this is again easy marks. A catalyst provides an alternative reaction pathway. Provides an alternative reaction pathway with a lower activation energy. And you can write this if you want to via the formation of intermediary bonds. And what I mean by via the formation of intermediary bonds is the catalyst does participate in the reaction, but the catalyst is not consumed in the reaction. It is only an intermediary bond with the reactants. Alright, so it provides an alternative reaction pathway. You can explain that this increases the proportion of particles with a kinetic energy. You probably want to write the full thing, not just EK, greater than or equal to the activation energy. So this increases the proportion of successful collisions and if it increases the proportion of successful collisions, hence the frequency of successful collisions. Therefore, a catalyst increases the rate of a chemical reaction. Easy. Okay. A mixture of gases, blah, 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 was at equilibrium. Sketch a labeled qualitative graph, all right, just demonstrating the changes in the rate of the forward and the reverse reaction if a catalyst was added at T1. Okay, so they want a graph. So it's important thing to note is this. Yes, a catalyst increases. In fact, I'm going to probably show it right here. So I'm going to draw an energy profile diagram first. So in an energy profile diagram, this is what it looks like basically. Here, and this. And we all know what a catalyst does. A catalyst just, I'll just write enthalpy on here. And we all know that the x-axis stands for progress of reaction. Okay, I won't bother with that for now. So obviously reactants over here and products over there. Now, what you need to understand is the catalyst provides an alternative reaction pathway with a lower activation energy. So basically, this is a catalyzed pathway, okay? This is a catalyzed pathway. You can clearly see is that it reduces the activation energy. It used to be this, now it's this. Now, the important thing you realize is not only does it reduces the activation energy of the forward reaction by around about this much. It reduces the activation energy of the forward reaction from here to here. So rather than going all the way up to here, it only has to go up here, so it reduced the activation energy by that much. Now it also, consider the reverse reaction. The products initially had this activation energy, now the products only have this much activation energy to go back. The point being, it has reduced the activation energy of the reverse reaction by the same amount. So what I want everyone to understand is that a catalyst, yes, it increases reaction rate, but we just discussed how it increased reaction rate, but a catalyst reduces the activation energy of the forward and reverse reactions by equal amounts. Forward and reverse reactions by equal amounts. And since it reduces the activation energy of the forward and reverse reaction energy by equal amounts, it means that the increase in forward equals the increase in reverse, aka no shift in the position of equilibrium. Catalysts do not change the position of equilibrium. They might reach equilibrium faster, but they definitely don't change the position of equilibrium. Okay, so back to this. Sketched a labeled qualitative graph demonstrating the changes in the forward and reverse reaction rate if a catalyst was added at T1. So basically what I'm saying is, it used to be at equilibrium until T1. Now we added a catalyst, and a catalyst simply increases the forward and reverse reaction rates by equal amounts. So it's basically like a ladder, and forward and reverse. Now be careful, they want you to draw like a solid and a dotted arrow, so pretty much you wouldn't do what I did. You'd like do forward like such, and then like completely right next to it you draw the exact same thing, and pretty much right on top of it, but you'd have to draw it dotted. I'm just doing it light blue for the purpose of this question. I'm going to do the reverse in light blue, but you can't do that in the test. You have to use the same key that they use. So this is me sticking with the light blue colors. Okay, so basically stays the same. Alright, forward and reverse reaction rate just don't change at all. Alright, pretty easy concept. Okay, that's pretty straightforward, and we should all understand that quite well. And hopefully this explanation justifies why, because we just showed how it decreased the activation energy by equal amounts, as shown by the red arrows, okay, the red segments. All right, question number 12. Now, question 12 is quite tricky. There is a trick to question number 12. The trick to question number 12 relates to the specific equation, and it relates to the K constant. This is what will allow you to see it really, really well. So this is solid, this is gas, which means that there is basically nothing on the reactant side. It's basically a 1, which means we don't include it. So the K constant is concentration of HCl times concentration of NH3. Now this is unique, all right? This is one of those full counteracts. This is one of those reactions where it's possible to do a full counteract, and you're going to see why, okay? So for each of the following changes, predict the effect on the value of the equilibrium constant. Now first thing first, what's the only thing that affects K? Only change in temperature affects K values. Only change in temperature affects the K value. And if only change in temperature affects the K value, so for this one, and this one, where it is not a change in temperature, I want to write no change, no change, no change. All right, without even thinking, I'm just going to write no change, no change, and no change. It does not affect the K value. Okay. Now, the rate of forward reaction. You'll notice that there is an important word that's not written there. It does not use the word initial. It did not say what happened to the rate of the initial forward reaction. It doesn't say that. And since it doesn't say that, it might as well just say what happened to the rate of reaction. Okay, it's got nothing to do with the year 12 stuff. It just means what happened to the rate of reaction. Okay, so that's the type of question or type of concept it is. So the first one, remove NH4Cl solid. Now this is a tricky one. Yes, we're removing this, and some people might think, oh, that's going to decrease the concentration of the NH4Cl solid. That is not true. It is a solid. Solids don't have concentrations. Solids have like a surface area to volume ratio, but they don't have concentration. All right. So if you remove some of this, and remember it's in equilibrium, I want you to guys consider exactly what's happening. There's basically a closed beaker. Inside this closed beaker there's some lump of NH4Cl solid. All right, and there is some HCl gas floating in the air, and there's some NH3 floating in the air. And when it reaches equilibrium, it simply means that the rate at which the NH4Cl becomes HCl and NH3, the rate at which NH4Cl decomposes, is equal to the rate at which the HCl and the NH3 return back and become NH4Cl. So if you remove some of this solid, it will not change the concentration of NH4Cl. It will not change the rate at which the NH4Cl decomposes or the rate at which it's resynthesized. So the removing of NH4Cl solid has no effect again on the position of equilibrium. All right, again, like I said, because it did not use the word initial, they might as well just say what happened to the rate of reaction. So what happens when you add a catalyst to the rate of reaction? There is an increase in reaction rate. What happens when you increase the temperature? It's got nothing to do with year 12 equilibrium. It's just got to do with year 11. What happens when you increase the temperature to reaction rate? There is an increase in the reaction rate. What happens when you increase the volume of a container? Now remember, increasing the volume simply means decreasing the concentration of all gas species. That means it is going to decrease the concentration. Alrighty. So, back to this. Removing some NH4Cl solid. We all agreed that removing NH4Cl solid, it didn't do anything to this. It obviously didn't do anything to the HCl, and it did not do anything to the NH3. So really, the concentration of NH3 is also no change. Alright, nothing really happens. I guess the only thing happens is that since you remove some NH4Cl solid, it simply reduces the mass of the NH4Cl solid. So that's a bit of a kind of where it didn't do anything at all. Add a catalyst. Now we just agreed that when you add a catalyst, it does not change the position of equilibrium. Catalysts do not change the position of equilibrium. So yes, the forward reaction rate goes up, but not only does the forward reaction rate go up, now don't write this is just for your knowledge, the increase in the forward is equal to the increase in reverse, and therefore no shift. Okay, therefore no shift in the position of equilibrium. And if there is no shift in the position of equilibrium, the concentration of NH3 does not change, and the mass of NH4Cl does not change. Great. Increase the temperature. What happens when you increase temperature? We all know what increased temperature means. It means that we're going to favor the endothermic reaction. It tells us the delta H is more than 0, so that is the endothermic reaction, so it means it favors the forward reaction. Now, if you favor the forward reaction, that effectively means that we increase the concentration of products. All right, not only do I was going to say we decrease the concentration of reactants, but there are no reactants. And since there are no reactants, when I say there are no reactants, there's no concentration of reactants, because remember, it's not even part of the K constant. So simply we favored the forward reaction, which means the concentration of HCl and the concentration of NH3 will both increase. And if the concentration of HCl and NH3 both increase, it means that the K value will increase, okay? So it is a change in temperature that will cause an increase in the K value. All right, obviously I just said we're going to favor the forward reaction when you increase the temperature. which means the NH4Cl solid will get consumed and therefore its mass will decrease. And obviously the concentration of NH3 will increase. All right, which brings us to the last one. And the last one's the tricky one. The last one is the important one. It is really, really important. All right, now, what most students may initially do is this. So let's have a look at it. Increase the volume of the container. Now, if we increase the volume of the container, I'm just going to write on the side. So we increase the volume of the container, which means we decrease the concentration of gaseous species, which means in this case, we decrease the concentration of products, not reactants, because the reactants don't have a concentration. We just agreed NH4Cl solid does not have a concentration. So if there is a decrease in the concentration of products, there is a decrease in the reverse reaction rate, okay? And no effect on the initial forward reaction rate. No effect on the initial forward. Now, here's the mistake that most students will make. Most students will accept that both the HCl and the NH3 will decrease. All right, and now what most students will probably do is they will think that, okay, this one went down, this one, same color, HCl went down, NH3 went down. So as per LCP, we're going to counteract the shift in the position of equilibrium. So to counteract it, we're going to favor the forward reaction. If you favor the forward reaction, HCl concentration increases, NH3 concentration partially increases, which means at the end of the day, this is less, this is less. This is what most students will do, because most students are taught that this is the definition of LCP. So what most students do, but then it is also incorrect, they will write this. So they will say that LCP states that equilibrium shifts to partially counteract the imposed change. The equilibrium shifts to partially counteract the imposed change. That is not the correct definition. Yes, most of the time it partially counteracts the imposed change, but not every time. So first of all, that is not Le Chatelier's principle. Le Chatelier's principle does not say that it's going to favor the equilibrium such that it partially counteracts the imposed change. What is the correct thing to say, which only few people say, only few students say the correct thing? LCP states that equilibrium shifts in such a way to counteract the imposed change. Equilibrium, like basically, I'm going to write it better. That LCP states that upon disturbance to a system, equilibrium is re-established I need to say this better. LCP states that upon disturbance to a system at equilibrium, the reaction, I don't want to say the reaction shifts. I want to just say that we're gonna, LCP states upon disturbance to equilibrium, the system reestablishes equilibrium reestablishes equilibrium in a way that opposes the imposed change. Now, the way it imposes the, I shouldn't really say opposes, but counteracts in a way that counteracts the imposed change. Now, here's the key thing. The key thing is not that it partially counteracts. That is not the key thing, which a lot of people think. The key thing is that the system reestablishes equilibrium. That is the key thing. It is not the partially counteract that's key. What is key is that the system reestablishes equilibrium. So it reestablishes equilibrium in a way that counteracts the imposed change. Now, when it counteracts it, that counteract might be partially, which is what happens in most of the questions, or the counteract might be fully, which happens in very, very few questions, such as this. Okay, there's a video that discusses all the different types of fully counteracts in equilibrium, the full counteracts. So equilibrium may be fully counteracted, or the imposed change may be partially counteracted, or it may be fully counteracted. Now I'm just going to prove to you why this is wrong. So just so we don't forget what happened. What happened was we increased the volume of the container, and that decreased the concentration of all gaseous species. So when it decreased the concentration of gaseous species, we decided to favor that decreased the concentration of these two things. So to counteract the imposed change, we favor the forward reaction. Now most people will only partially counteract it because that's what they're taught, which means most people will say that at the end of the day, the concentration of HCl and NH3 decreases still. Now remember, did we change temperature? No. And since we did not change temperature, did we change the value of K? No. There was no change in the value of K. Now, according to this thing that I've done, which is wrong, by the way, so I'm just going to write down that this is wrong, and then I'm going to write down what is the right thing to do, and let me copy paste the K constant. Now, why is it wrong? It is wrong because at the end of the day, we agreed K does not change. But apparently, we've just said that at the end of the day, the HCl decreases and the NH3 decreases. If the HCl decreases and the NH3 does an overall decrease, that means both these are less than what they used to be, which means K is less than what it used to be, which suggests that a change in temperature, not a change in temperature, that suggests an increase in volume, which is not a change in temperature, decreases the K value. That is wrong. How can this drop and hence K drop if there is no change in temperature? So this is what I'm trying to say. What I'm trying to say is, yes, we decrease the temperature. Sorry, I keep saying temperature. We increase the volume, aka decrease the concentration of HCl, and decrease the concentration of NH3. Now what I'm claiming is that it must come back up all the way. It must come back up all the way, which means at the end of the day, there is no change in the concentration of HCl, and there is no change in the concentration of NH3. So if there's no change in the concentration of that and no change in the concentration of that, that would mean that there's no change in the K value. And we 100% agreed that because there was not a change in temperature, there was no change in the K value. And if there's no change in the K value, it means these must fully counteract. So I hope you guys realize the key thing was not partially counteract. In fact, partially counteract is wrong. The key thing is that we need to reestablish equilibrium. All right, in a way that counteracts the imposed change. So in this case, it fully counteracted the imposed change, and the concentration of HCl and NH3 went right back up to what they were. So at the end of the day, the concentration of NH3 has no change. There was no change in its concentration. But we did favor the forward reaction in order to counteract the change, and just rub this out. So the correct thing to have drawn would have been, yes, these guys' concentration decreased, hence we favored the forward reaction, and the forward reaction caused a full counteract in the concentration of HCl decrease and the concentration of NH3 decrease, and by favoring the forward reaction, it decreased the amount of NH4Cl solid. So the mass of NHCl4 solid does decrease. So that's one of the unique full counteracts. A lot of people would have got that wrong. Now, while I'm on that concept, I just want to show a few things related to that. So first of all, I want to show a concentration versus time graph. A concentration versus time graph, and I'll also do a reaction rate versus time graph. and specifically for an increase in the volume. So a reaction rate versus time graph. Now, what did we have? We had HCl and NH3. Okay, since each NH4Cl breaks up into one HCl and one NH3, it means they have equal concentrations. Okay, so I'm just going to draw one single arrow for both the concentration of HCl, aka the concentration of NH3. Now remember what happened. We increase the volume. If you increase the volume, there is effectively a decrease in the concentration of both gaseous species, which means both these HCl and NH3 decreased. Okay, and what did it do? It did a full counteract. It did a full counteract and came back up right up to what it was. It didn't partially counteract, it did a full counteract. Now the key thing other than the full counteract is the following. Why does it decrease? Why is it that there is a decrease in the concentration of NH3? It's because there's an increase in the volume. Because there's an increase in the volume, hence there is an immediate decrease in the concentration of gaseous species. Now remember, all you did here was make the container bigger. So when you make the container bigger, the volume goes up, the concentration of gas goes down immediately, but there is no effect on the number of moles of the gas species. Okay, all you did was make the room bigger. Then what happened over here? What is happening in this section over here? In this section over here, while it like from here, basically from this point here to this point here, what is it doing? It favors the forward reaction. We are favoring the forward reaction. Both of these dropped, so we favored the forward reaction in order for the HCl and the NH3 to come back up. It just so happened to be that they came back up to their original concentration. So if you favor the forward reaction, what you need to understand is you are actually increasing the number of moles of gas by favoring the forward reaction. And if you increase the number of moles of gas, that's what caused an increase in the concentration of gas species. Okay? And that's why at the end of the day, therefore, there was no change in the concentration of any gas species. So what I'm trying to say is this. The concentration of gas went down and came back up to right to what it was, which means that at the end of the day, the concentration of HCl and the concentration of NH3 is unchanged. All right? But, here, nothing happened to the moles, and then you favored the forward reaction and increased the number of moles. What I'm trying to say is despite the concentration of HCl and the concentration of ammonia not changing, the moles of HCl and the moles of ammonia did increase. And we all understand that concept, that concentration is different to moles and they don't have to necessarily do the same thing, especially with questions involving a change in the volume. So that's a very, very important concept that we all need to know. All right, let's draw a reaction rate versus time graph. So both forward and reverse reaction rates were equal to begin with. Then what did we do? We increased the volume. Now remember, what's volume going to do? Volume is only going to affect gases. It does not affect solids. It only affects gases. Since it does not affect solids, it does not affect the initial forward reaction rate. It only affects the initial reverse reaction rate. So what we need to understand is the forward reaction stays exactly where it is. It does not move at all. Whereas the reverse reaction rate immediately decreases. It immediately decreases at that point. All right, there is a decrease in the reverse reaction rate. Why is there a decrease in the reverse reaction rate? It's because there is a decrease in the concentration of gas species. Okay? All right, forward stays put. Now remember, this doesn't now come back down, and what we're used to is this coming back down and this coming down and meeting up together again. But remember, at no point does the concentration of NH4Cl solid change. Even as we favor the forward reaction, the concentration of this does not change. It is a solid that does not have a concentration, which means that since the NH3 and HCl return to their original concentration, their concentration dropped, and that's why the reverse reaction rate dropped. And because they returned to their original concentration, equilibrium, the reverse reaction rate comes right back to the same as the forward rate of reaction, which means that at the end of the day, there is no effect on the concentration of there is no effect on the forward and no effect on the reverse reaction. That is a very, very tricky concept, because what's the first thing that I did? I just considered year 11 knowledge. And according to year 11 knowledge, I just thought that if you increase the volume of the container, reaction rate has to drop, because that's what we're taught in year 11. But you can clearly see that, yes, the reaction rate dropped, but it's a weird one. The forward just did not change, and then the reverse reaction rate came right back up to what it was, which means I need to change this answer to no change. So that is a tricky concept. It is one of those full counteract question types, and you can see in this reaction rate versus time graph exactly why the eventual forward reaction rate is the same as what it used to be. Okay? Perfect. Refer to the video on full counteracts, and there's a few more examples of that. It goes through all the different types of full counteracts. All right, predict the observation made, if any, if the temperature was decreased. Okay, and it says use collision theory, and it's worth 6 marks. Okay, so what we can explain, again, I'm just going to use short words. In the test, you probably have to use sentences. A decrease in temperature causes a decrease in the kinetic energy of all the reactant and product particles, of reactants and products, which causes a decrease in the proportion and frequency of successful collisions. Decrease in the proportion and frequency of successful collisions. I'm only writing so much because it's worth 6 marks, which causes a decrease in the rate of reaction. And specifically, it causes a decrease in the forward rate of reaction and a decrease in the reverse rate of reaction. So that's the first thing I'm going to write down. Probably would have used a few more words, but yes. If the temperature, okay, so that's the first thing I'm going to write down. Next thing is the following. Okay, so it says predict the observations made, if any, okay, and use collision theory to explain the effect. So we can explain, we all know that the endothermic reaction is always more profoundly affected. So which one's endothermic? Delta H more than 0, that means the forward reaction is endothermic. So what we can write is that the decrease in the forward endothermic reaction is more profound than the decrease in the reverse exothermic reaction. More profound than the decrease in the reverse exothermic reaction. What I'm basically saying is that the decrease in forward is more than, the forward drops by more than the reverse. And if the forward drops by more than reverse, the reverse is greater than the forward reaction rate. And as reverse is greater than the forward reaction rate, we can explain, I have to explain why. Okay, sorry. The forward reaction rate is more profound than the reverse reaction rate, as the forward endothermic reaction has a higher activation energy. As the forward endothermic reaction has a higher activation energy. So, as forward is more than reverse, equilibrium shifts to the right. And if equilibrium shifts to the right, what would we observe? Therefore, a decrease in the mass of NH4Cl solid, which means if there's a decrease in the mass of NH4Cl solid, and we all should know that ammonium chloride is a white solid, we can explain, hang on, just make sure. Okay, whoops, I made one mistake again. The decrease in forward is more than the decrease in reverse, which means that the reverse is higher than the forward reaction rate. It means the reverse is higher than the forward reaction rate, which means equilibrium shifts to the left, which means that in fact there's actually an increase in the mass. Okay, so that's the mistake I made. Bit of a silly mistake, but I specifically said that the decrease in forward is more than the decrease in reverse, and that means reverse is more than forward. And if reverse is more than forward, it means equilibrium shifts to the left. Okay, so if equilibrium shifts to the left, there is an increase in the mass of this, and remember we have to bring it to observation. So therefore, there's going to be an increase in the mass of that mass or size, if you have to write observations. Increase in the, I'm going to write size to be clear because that's an observation. Increase in the size of the white solid. Increase in the mass of the white solid in at the bottom of the beaker. Okay, bottom of the vial, glass vial. Now, a lot of people made a silly mistake. So technically, if you favor the reverse reaction, we're going to lose that NH3. We're going to have a reduction in this pungent smell of NH3. Now, the trick is, a lot of people said that there's a decrease in that pungent smell, but it says that's in a sealed glass vial, and because it is in a sealed glass vial, we should not be talking about smells at all. Now, both NH3 and HCl are colorless gases, so we wouldn't observe anything. The only observations we would see is a increase in the size of the white solid. Perfect. And that's full marks using collision theory. So I explained why temperature causes a decrease in reaction rate. I specifically discussed both the fact that it affects the proportion of successful collisions and frequency of successful collisions. If your teacher is really picky, then you probably at this point should write that this causes a additional things you can write is this causes a decrease in the proportion of particles with a kinetic energy less than or equal greater than or equal to the activation energy, and it causes a decrease in the velocity of the particles. Alrighty, we should really write that down. And remember that since the decrease in proportion of particles is what causes a decrease in the proportion of successful collisions, whereas the decrease in the velocity of the particles is what caused a decrease in the frequency of successful collisions. So that's worth 2 marks. Another mark to say that both forward and reverse will drop, except that the forward drops by more than the reverse because it has a higher activation energy, because the forward is endothermic. And since reverse is more than forward, equilibrium shifts to the left. Okay, and then the last mark for explaining that decrease in the mass of NH4Cl solid as decrease in the mass as it is deposited. Always got to write this down, as it is deposited at a faster rate than it decomposes. Faster rate than it decomposes. Until equilibrium is reestablished. Okay, nice concept, nice question. Okay, next one. Methane reacts with hydrogen sulfide to produce carbon disulfide and hydrogen gas. Okay, fine. Alright, complete the concentration time graph. So, initially, 4 moles of CH4 is added to 3 moles in a 1 liter flask. Now, I like the fact that it's a 1 liter flask. The fact that it's in a 1 liter flask, now just remember, concentration is N on V, but because it's a 1 liter flask, the volume is 1, which basically means the concentration is the number of moles. Now, this is a question where using an ICE table is really helpful, all right? It just makes the question much easier. So, in my ICE table, all right, I stands for initial concentration. C stands for the change in the concentration, and E stands for the equilibrium concentration. So that's why it's called an ICE table, ICE. So what do we have in my ICE table? We have CH4, we have 2H2S, CS2 and 4H2. So initially, at T0, 4 moles of CH4 is added to 3 moles of H2S. So what I'm able to do is put 4 moles per liter here and 3 moles per liter there because concentration equals number of moles, and obviously 0 moles of this. All right, it says the mixture reaches equilibrium, and at equilibrium there is 1 mole of CS2. So there is 1 mole of CS2, so at equilibrium there is 1 mole, which means that the CS2 went up by 1. Now remember, the way it works is one of these reacts with 2 of these to make 1 of these and 4 of those. The point I'm trying to make is that the change in equilibrium has to be proportional to the Stoic ratio. So 1 to 2 to 1 to 4. That the change must be in the ratio 1 to 2 to 1 to 4. So if CS2 goes up by 1, now remember these are reactants and therefore their concentrations are dropping, and these are products, therefore the concentrations are increasing. The CS2 increased by 1, so the H2, which has got a 4 in front of it, has to increase by 4. All right, this one's got a 2 in front of it, so it's got to decrease by 2. And the CH4 has got the same ratio as the CS2, so if the CS2 goes up by 1, the CH4 goes down by 1, which means the final equilibrium concentrations are 3, 1, 1, and 4. Perfect. That makes this question really, really easy. That's the first part anyway. So that's the first part done. When I say the first part done, that's the part that's talking about the mixture reaches equilibrium at T1. So by the time we reach T1, we are at equilibrium. So let's just write down what happened all the way up to T1. T1. All right, so we started at 4 moles per liter CH4, and it eventually became 3 moles per liter, and that's T1. Sorry, that's the H2, that's CH4, started off as 4 moles per liter and finished off as 3 moles per liter, and then it stayed at equilibrium until T2. What else did we have? We had H2S that started at 3 and finished at 1. So if H2S starts at 3 and finishes at 1, that will look something like this. And then it stays at equilibrium until T2. We'll label that H2S. Now, both of these started at 0. This one went all the way up to 1, so CS2 went up all the way to 1. So we'll draw it here, and right there. So same really as the other one. And H2 started at 0 and finished at 4. So starts at 0 and finishes at 4, so all the way up to here. We want it to get flat by the end, so that's better. Okay, and it stayed at equilibrium for a while. Okay, so that's up to T2. All right, that is my first ice table. Now, I'm pretty sure I'm going to need a second ice table because they do something else. Equilibrium is maintained until T2, and now at T2, 1 mole of H2S is added. Okay, so 1 mole of, I don't think we'll need an ice table because all they tell me is 1 mole of H2S is added. They don't, I'll get away with just doing this. So 1 mole of H2S means that we're going to go from 1 mole per liter to 2 moles per liter. So if we increase the amount of H2S, what are we going to do? That's going to cause us to favor which reaction? If the H2S goes up, we're going to favor the forward reaction to re-establish equilibrium. Because there are species on both the reactants and the product side, because this and this are all going to be in the K constant, it is not a full counteract, it's just our normal partial counteract question types. So if you favor the forward reaction, this one partially decreases, this one decreases, this CS2 increases and the H2 increases. Okay, so that's what's going to happen. We don't need to know in what ratios they do. Sorry, we don't need to know how much specifically, as long as we follow the ratio 1 to 2 to 1 to 4. So all I need to show is that this has gone up and then it's going to come back down partially. So if it comes back down partially, all we need to do is show that it drops by a certain amount. So let's just say it drops by that much. So, and what happens at T3? It says, yes, equilibrium reestablished at T3. And where do they want me to? I guess I'll continue a little bit beyond that point and just stay flat. So that's it going up and coming back down. What I'm going to do is call this amount here x. So at the end of the day, it came back down by x. So if CS2 comes down by x, sorry, not CS2, if H2S comes down by x, this small change is x, that would mean that CH4 drops by half x, and it means that the CS2 goes up by half x, and it means that the H2 goes up by 4 lots of this. You know, it's going to be easier. Rather than calling this x, it's just confusing to have half there. What I'm going to do is say that the H2S goes down by 2x. If the H2S goes down by 2x, it means the CH4 goes down by x, and it means that the CS2 goes up by x, and the H2 goes up by 4x. It will just be easier to work with. So over here, what I'm going to say is that this is, yes, the H2S went up, and then it came down by 2x. What else went down? The CH4 went down by x. So I'll draw something similar and make it go down by x as well. Now, just to make it look a bit more accurate, now if this is x, clearly the 2x doesn't look very well scaled. So if this is my x, then really I should make the 2x a bit lower. That looks a bit more like 2x. Okay, so that's 2x. Okay, so back to where I was. The CS2, the H2S went up, then it came back down by 2x. This one came down by x. CS2 goes up by x. So let's draw the CS2, which is the purple one, going up by roughly x. That would be roughly around about here. Then it stays at equilibrium, so flat line from that point here. We'll just label it x. So it doesn't have to be perfect, and the fact that I'm using a scale, I'm not scale, but I'm using the x's, it really helps specify the ratios. And lucky last, the H2 goes up by 4x. So if this is 2x, which is almost half a block, so 4x would be the entire thing. So we would want this to go up all the way to here, and then stay put. And we can say that this is 4x. Perfect. Okay. Nice question. 5 marks. Pretty straightforward one. Okay. And the system obviously reestablishes equilibrium at T3. So T1, it reestablished equilibrium, which is why everything was flat. And at T3, it reestablishes equilibrium, which is why, again, all concentrations are constant from that point. All right. A moderate temperature and pressure and use of catalyst are used. Discuss the choice. All right, 2 marks. So why are they using a moderate temperature and moderate pressure? All right, and using a catalyst. So what we can explain is that a high temperature favors a high reaction rate, favors a high rate of reaction. Now, don't forget what the whole purpose of this reaction is. The whole purpose of this reaction is to make carbon disulfide and hydrogen gas, aka make some products. So, by having a high temperature, it favors a higher rate of making the products. However, you need to understand that the forward reaction is endothermic. And what favors the endothermic reaction? What would favor an endothermic reaction? High temperature favors a high temperature favors the forward endothermic reaction. Favors a forward endothermic reaction and increases the yield of product. Increases the yield of products. So now this is weird a little bit, right? It's weird because a high temperature is good for reaction rate. A high temperature is good for the yield. So surely, therefore, we should use a high temperature. All right. Yet they're saying moderate. Now, I would have said in my test, if they didn't say moderate, I would have said we're going to use a high temperature. Because remember, we have four options. We have low, we have moderate. This is both for temperature and pressure. We have low, moderate, high, very high. Now, we never use very high because it's expensive and unsafe potentially. The question only wants us to discuss rate, yield, and cost. So, high temperature favors reaction rate. High temperature favors high yield. So it just makes sense to use high. But because it says cost and because it says moderate, all right, and only, I guess more importantly, because it says moderate, it's not even the cost so much. So the cost is why we don't use very high. But the fact that it still nonetheless says moderate, we can explain a moderate temperature is used. A moderate temperature is used to achieve a compromise between reaction rate yield and costs, production costs. And specifically what we can explain is that lower temperatures reduce costs. Now, honestly, if what I would have done in my test, had they not used the word moderate, if the word moderate was not there, I would have said the following. So I would have copied the first two lines down still. I would have copied the first two lines down. Again, remember, this is only what I would have said if it did not say the word moderate. So we can write, therefore, high temperatures used to maximize reaction rate and yield. To maximize reaction rate and yield of products. All right, and specifically I would have said a very high temperature is not used to reduce production costs. And obviously to keep it safe. But there is no mention of safety here, so we won't discuss it. A very high temperature is not used to reduce production costs. All right, that's what I would have written. But because it said the word moderate, I wrote a very similar answer, but just basically wrote moderate instead. Okay, pressure. So what we can explain is that a high temperature favors high rate of reaction. Not temperature, sorry. High pressure favors a high rate of reaction. And it's only 2 marks. I'm not writing too much, but we all know why it favors a high rate of reaction, because it increases the frequency of collisions because of the high pressure. All right. Then, what do we have? How many gases do we have? We have 3 gases on this side, and we have 1 CS2 and 5 gases on that side. So, what we need to understand is what would favor the forward reaction. What would turn 3 gases into 5 gases? And I hope you guys realize that this is basically the side with more gas. So the question is, what type of pressure conditions would favor the side with more gas? And the answer is a low pressure. We can explain that a low pressure favors the side with more gases, and as there are 3 gaseous reactants and 5 gaseous products, a low pressure favors the forward reaction rate. Favors the forward reaction rate, okay, aka an increased yield of products. So a high pressure is good for reaction rate, a low pressure is good for yield. So therefore, this is what we're more used to. We can explain that a moderate pressure is used. Moderate pressure is used to achieve a compromise between rate of production of products, rate of production of, what are our two products? Rate of production of CS2H2 and equilibrium yield of CS2H2. Okay, that's why we use a moderate temperature. And you can explain that a pressure. A moderate pressure also keeps operation costs lower. Alright, and that is a mistake here. So it says moderate temperature, pressure, and use of catalyst. So there's temperature, there's pressure, and for whatever reason the written cost, what they mean is catalyst. Okay, so what do we need to discuss? Discuss the choice of these conditions with the reference to rate, yield, and cost. Okay, so we can explain that a catalyst increases the rate of reaction. Yes, a catalyst increases the rate of reaction. I'm not going to explain why, we all know why, without affecting the equilibrium yield. So that's one thing. And you can explain, although catalysts are expensive, they can be reused, right? Catalysts are expensive. They are not consumed in a reaction, and if they are not consumed in a reaction and hence can be reused. And what that does, which increases the cost efficiency in the long term, which improves the cost efficiency in the long term. Alright, so this is a typical question where we have an industrial process, and you have to discuss what type of temperature to use, what type of pressure to use, and whether or not to use catalyst, okay? And generally, again, this one was a bit different, but generally, if the way it works is if whatever it is. So let's just say that high temperature increases, we wouldn't even say temperature, high temperature or high anything. Let's say a high causes a increase in reaction rate and causes an increase in yield. Therefore, I will always use a high temperature or pressure and not very high to keep the operation costs low, and not very high to reduce costs, and for safety. Okay, that's one thing. And the second thing is, let's say high is good for high reaction rate, but low is good for high yield. Therefore, I will always use moderate. And the reason for the moderate is to achieve a compromise, between rate of reaction and product yield. That's how it works. I never use low. It's either moderate if they're in different directions, as in high is good for reaction rate, but low is good for yield. But when high is good for both reaction rate and yield, then I'll end up using high temperature or pressure, okay? And always use a suitable catalyst if possible. Okay, perfect. And that's the end of that test. Well done.